Hello everyone, I am Yash Jadhav. In this short demo, I will walk through the system architecture, demonstrate the synchronization engine, and explain the engineering decisions behind the implementation. So let us first go through the architecture. So the project consists of three major components. First is the controller application, which allows an operator to control playback. Second are the multiple display clients that stay synchronized. Third is the socket IO coordination server, which acts as the authoritative source of truth for the entire playback session. Every display continuously synchronizes itself with the server rather than communicating directly with each other. This makes the architecture scalable and much easier to manage. So let us now open the controller. So let us first walk through the landing page. So basically this is the system architecture. So first the front end has the controller, which works for the host initialization. The host launches the authoritative controller UI, establishes a WebSocket connection to the cluster, and initializes the master timeline. The second comes the Node.js and Redis-backed. It acts for the state backplane. The server acts the source of the truth, distributing play, pause, seek events globally via Redis PubSub to scale across the infinite node instances. The third comes the displays, which is again on the front end side, which has the client connection and NTP sync, which displays the connect and immediately brings a continuous NTP ping pong handshake with the server to map instantaneous network latency, which is RTT. Then comes the edge compute, which is one dimensional Kalman filtering. The client feeds noisy network offsets into a local 1D Kalman filter, stripping out jitter to output a mathematically stable clock offset. Now comes the global state party, which has a continuous rate of adjustment. Using the filter clock offset, each display accurately calculates the master's exact playhead. If the local video drifts occurs, the playback rate is micro-adjusted seamlessly until the perfect parity is re-established. So let us now walk through the controller. So here in the controller, I have pre-embedded 4 of the media, which is Big Bug Bunny, Elephant Trim, Sintel Trailer, and Tears of Steel, which is now running in the backend. Now, if I launch the display, here I have two independent display clients. First I am launching the first one, second, here it goes. Okay, and if I play the using the transport controls, it takes some time in the state to get paused and played. We can actually unmute. Yeah, each client periodically reports its local playbacks state back to the controller. Here you can see the state. You can see this first display, which is now playing the current state and has its clock drift of around 1600 seconds. Okay, the interesting part of this project is not simple sending play and pause events over WebSockets. The focus was building a synchronization engine similar to what would exist in a production distributed system. Instead of trusting a raw WebSocket latency, I implemented an NTP-inspired 4 timestamp handshake. First, the client has the starts at the T0, then the server goes for the T1 and T2 seconds, and after the T3 second, the video actually runs. Using this timestamp, the client estimates the actual clock offset between itself and the server. This gives much more accurate synchronization under varying network conditions. Now coming to the Kalman filter, network latency constantly fluctuates, as you can see here. Instead of reacting to every latency spike, I fed the measured offset into the lightweight one-dimensional Kalman filter. The filter smooths jitter and continuously estimates the true server clock. This creates a much more stable synchronization signal. Now coming to the drift detection, here you can actually see the diagnosis in each of the display, which has its RTT, clock offset, jitter, playback rate. Every client periodically reports its playback position. The controller compares this against the expected playback position computed from the authoritative server clock. The difference between these values is the synchronization drift. Instead of immediately seeking whenever drift occurs, I classify drift into two categories, which is a small drift and the large drift. If the drift is relatively small, I temporarily adjust the playback speed between approximately 0.95x to 1.05x. This allows client to smoothly converge without visible jumps. Now comes the large drift. If the drift exceeds the threshold, the client performs a hard sync to immediately recover synchronization. This hybrid approach provides both accuracy and much more smoother user experience. Now coming to the Redis architecture, you can see. Okay, the application also supports the Redis using the socket.io Redis adapter, which is integrated into the front end using the next public socket URL. This means the multiple Node.js servers can share synchronization events. Since playback state is authoritative and shared using Redis, the application can scale horizontally behind a load balancer without requiring sticky sessions. Now we will open the Playwright. Okay, here it goes. I also included automated Playwright test. These launch multiple browser instances, simulate playback, wait for synchronization to stabilize, and verify that the drift between independent clients remain within the acceptable limits. This gives confidence that synchronization continues to work correctly after future changes. I will walk through the code. Okay, here are the folders which we can see as the components, servers, sockets, and services. I separated the application into clear layers: the UI components, the socket communication, the session management, the synchronization logic, drift correction, and the state management. This keeps responsibility isolated and makes the synchronization engine easier to extend. Overall, my objective was not just to satisfy the functional requirements, but to build something that resembles a production ready synchronization engine. I enjoyed working on this challenge because it combines distributed system, networking, real time communication, and front end engineering into a single project. Thank you for reviewing my submission, and I appreciate your time and look forward to your feedback. Thank you.